Imagine sprinting through a gauntlet of monolithic, brutalist concrete slabs that tower 100 feet into the morning sky. These concrete slabs function as the primary kinetic components of a colossal, shifting machine. The audible grinding of stone is accompanied by severe vibrations that rattle the runner's body. We are witnessing a mechanical contradiction, a highly advanced brutalist superstructure driven by entirely primitive components. The threat here is the massive kinetic energy required to force these walls into motion. At the base of the tracks, massive stone gears drive directly against the concrete. Stone sliding on concrete typically produces dust, but we see intense showers of friction sparks, evidence of a violent conversion of mechanical work into heat. To understand how this system operates without tearing itself apart, we must build a first principles physics model. This model must account for three specific variables: structural mass, surface friction, and mechanical torque. Believability in this space requires a rigorous adherence to the laws of mechanical engineering. We begin by isolating a single 100-foot wall segment for dimensional analysis. Structural-grade concrete has a baseline density of approximately 150 pounds per cubic foot. Measuring the volume of this monolithic slab reveals a mass of thousands of tons per section. This downward force creates immense static friction, locking the base of the wall to the ground. The energy required to overcome that friction and initiate movement surpasses the output of the world's heaviest industrial machinery. At this scale, inertia scales non-linearly. Moving the slab requires force exponentially higher than what is needed for standard architecture. Because of this mass, the drive mechanism is engineered to prioritize extreme torque over speed. Let's analyze the massive stone gear interface at the base of the structure. While modern engineering would use hardened steel, these architects utilized primitive, unreinforced stone. Stone possesses very low tensile strength. Our vector schematic shows how shear force accumulates at the base of each gear tooth under the load of the slab. To prevent the teeth from snapping, they must be engineered significantly wider and thicker than steel counterparts. Distributing the kinetic load across a flat concrete rail allows these thickened teeth to move the slab without structural failure. Any mechanical misalignment in this gear train would lead to an immediate cataclysmic jam. The oversized, brutalist aesthetic of the gears is a direct result of using stone to move such immense mass. Consider the moment those stone gears engage the track at high speeds. The friction coefficient of stone grinding on concrete is extremely inefficient, resulting in a violent interaction between surfaces. This friction triggers material spalling, causing the structural surface to fracture and send heavy clouds of concrete dust exploding outward. We must also account for the brilliant flashes of friction sparks seen during movement. Pure stone and concrete do not typically generate sparks. This cross-section reveals why it happens here. For sparks to fly, the gears must be actively grinding into internal steel rebar or high quartz aggregates within the wall. These visual effects are the thermodynamic byproducts of structural materials failing under extreme kinetic stress. That stress extends beyond the gears and into the surrounding floor. The mechanical torque required to move the wall transfers excess kinetic energy directly into the foundation. This transfer generates Rayleigh surface waves, mechanical vibrations that radiate outward through the ground. As the gears accelerate, these waves increase in amplitude, causing the surface of the floor to displace upward. This upward displacement is what causes loose debris to lift and bounce off the ground. This heavy seismic response serves as a structural warning system, signaling mechanical movement across the entire expanse of the labyrinth. The drive mechanism effectively functions as a vibrational engine, turning the surrounding bedrock into a mechanical resonator. The final stage of this mechanism is the rapid, claustrophobic closure of the maze. Bringing thousands of tons of inertia to a sudden stop creates a massive spike in structural stress. To leave a precise 2-foot gap, the system must apply total braking force at the exact microsecond before the final impact. This instant locking subjects the gears to an extreme G-force spike as they absorb the wall's remaining momentum. Successfully stopping these walls without shattering the gears presents a significantly higher structural challenge than the initial acceleration. We are focused on the microsecond the doors finally halt. The accumulated kinetic energy is released in a massive acoustic and structural shockwave. The resulting thunderous boom is that energy transferring from the locked gears back into the static walls of the labyrinth. A runner dives through the remaining 2-foot gap as the massive concrete doors slam together with a violent final force. The terror of the shifting labyrinth is rooted in the unyielding laws of macro-scale physics.